At some point today, we're going to have a visitor from the Air Force come and talk about scholarships that are available. They're supposed to be here, but I think they're not here yet. So I'm going to talk about a regular lecture, and then at some point it's going to be interrupted by that lecture, and then we'll continue on. It should take about 5 minutes, so we'll continue on with the rest of the lecture after that. Okay, so where we left off on Monday, we're looking at this amplifier model, and we're trying to figure out if this is a good audio amplifier. Okay, so remember the range of audio frequencies is roughly 20 hertz to roughly 20 kilohertz. And when we looked at this circuit, we first looked at the input part of the circuit, and we found out the input transfer function, which was given by this, and that is a low pass transfer function. And the 3 dB frequency is equal to 1 over 2 pi times the time constant, and the time constant is the R1 times C1, and that gave about 16 kilohertz. Then we looked at the transfer function at the output side. So if we look at only the output side, in order to get from circuit to this circuit, do a source transformation with the current source, change it to a voltage source, and then you move the position of resistor R2. And then if you look at the transfer function of this output side of the circuit, that is the voltage across R3 divided by VI and that is the voltage of this source normalized to VI, because I moved VI over to the left-hand side of the equation. And then I'm doing a voltage divider between R3, R2, and C2. So R3 is in the numerator, and all the impedances are going to be in the denominator. And the 3 dB frequency again, it's 1 over 2 pi times the time constant. And for this circuit, well, the time constant is always RC, but I have two discrete R's. So it's R2 plus R3 times the capacitance, which is C2. And this comes out to 53 hertz. Okay, that's where we ended. So is this a good audio amplifier? By the way, this is a high-pass circuit. Who says this is a good audio amplifier? Who says it's not a good audio amplifier? Okay, more people said it's not good. Why? Can someone then justify why it's not good? Because I won't hear. Sorry, I can't hear you. I need an audio amplifier. Yeah, I won't be able to hear 20 hertz because it's acting like a high pass, and the break frequency of this high pass is at 53 Hertz. So anything below that, I'm not getting the same amount of gain. So it'll work as an audio amplifier. I'll be able to hear most of the audio tones, but it won't be a good audio amplifier because I'm going to cut out, the very low bass side of whatever audio is coming through. And that's also true if I look at what's happening at the input side. So the input side, I had to cut off the low pass. By the way, I'm plotting the magnitude of the transfer function. So these versus frequency. Sorry, I didn't label the graphs. These are Bode plots. And that cutoff is at about 16 kilohertz. So this amplifier circuit is also cutting out the very highest frequencies as well. So it'll work as an audio amplifier, but it won't be a good one. Okay, so we looked at it in parts though. Let's describe the overall transfer function. So I'm going to call that just T of S. And so that would be the input transfer function multiplied by the output transfer function. And so the input transfer function was 1 over 1 plus S R1C1. And the output transfer function is negative GM R2 multiplied by R3 for R2 plus R3 plus 1 over SC2. Or another way of writing this would be keep the input transfer function the same, and it would be negative GM times R2 in parallel with R3. And if I do that, then my last term is going to look like this. So that's more clearly the form of a high pass circuit. Okay, so I have a low pass at the input and a high pass at the output. And so if I'm going to draw the overall Bode plot, I'm going to draw that on the next slide. Wait till everyone's done writing. Or wait till this guy's done drilling. Okay, so I'm going to plot. Oops. Oh, it's not T, it's just T. I'm doing the Bode plot for my amplifier, for the whole amplifier, including the input and the output. So the transfer function of this whole amplifier. Okay, so I have two breakpoints, and those are at what frequencies? 53 Hertz and 16 kilohertz. So between those two frequencies, my gain will be constant. At frequencies lower than 53 Hertz, my gain is going to decrease. my gain is going to decrease because of the output transfer function. And at frequencies greater than 16 kilohertz, my gain is going to decrease because of my input transfer function. And what's this decrease? What's the slope? These are single order or single time constant filters. One pole. You must have covered this in EE323, right? Is this the first time you're seeing this? Have you all seen this before? Okay, it was a while ago, but it's still a prerequisite. So if I have one pole, that corresponds to those break frequencies. So one pole, after the break frequency, my slope is going to be what? Minus 20 dB per decade. Same thing at this point. This is minus 20 dB per decade. And if I wanted to then label the 3 dB bandwidth of this amplifier, it's going to be 16 kilohertz minus 53 hertz. That's still about 16 kilohertz. Okay, so this is my 3 dB bandwidth. And so like we said, it will amplify audio, but it's not a good audio amplifier because I'm losing, or the gain at the very low frequencies is not the same as what it is in the middle of the audio range. And same thing at the high frequencies. I'm losing some gain at the higher frequencies. So I don't have the very lowest bass and I don't have the very highest treble coming out of this audio amplifier. Any questions on this example? Okay, so all of this applies generally to any type of amplifier. All you have to do is make the equivalent circuit model for whatever amplifier you have, and you can do all of this analysis for anything. So what we're going to do for the rest of this semester, we're going to look at more specific examples of how you would actually make an amplifier. So right now we know how to model it, and we know how to look at its behavior, but we don't know how to actually make an amplifier. So we're going to look at that in increasing steps of complexity. So first we're going to talk about op amps, which you've already covered in some detail in 211 and 213. It's an amplifier that's already made for you. You just need to make the feedback network in order for it to work as an amplifier. So that's the simplest case we're going to look at. Then we're going to look at transistor amplifiers. In that case, I'm just starting with a transistor. So you have to make a circuit that allows it to be an amplifier. Because a transistor by itself, you can use it as a switch or you can use it as an amplifier. It depends on what kind of circuit surrounds that transistor. Okay, so I'm going to talk about op amps now. So we're going to move to the next set of notes. And this is the summary of what we're going to talk about for this topic. We'll talk about the ideal op-amp, inverting and non-inverting op-amp, and this is hopefully a review. Then we'll talk about difference amplifiers, both single stage and multi-stage, and we'll then talk about what happens in a real op-amp. So all of this is for ideal op-amps, and then we'll talk about some practical issues that occur when you use op-amps. And we need to know the imperfections in op-amps before we can look at the final configurations of op-amps that we'll cover, which are integrators and differentiators. Okay, so like I said, now that we know how we can model an amplifier, we still don't know how to actually make one. Because, for example, the voltage amplifier model, I have a resistor there, I have a dependent voltage source, and another resistor here. But I don't know how to actually make it. How do you make a dependent voltage source? We've never learned that, so we don't actually know how to make an amplifier. But you can make an amplifier using an op-amp. But I think this is a good point to take a break, and then now we're going to have a presentation on some scholarships offered by the Air Force. Come on. Have your slides. Yeah.